that. You guys seeing my screen?
We are.
Okay, excellent. So what I'd like to start with first is I'd like to get a little bit of a feel for the group. Units 2 and 3, which is what I was suggested to review today, are a huge broad topic and we have an hour, so that is not going to happen. So please type in the chat a number, students, 1 through 4, or 1 through 5, sorry, of which of these things you would most benefit from reviewing today. And that's where we'll start to make sure that we cover that topic. Okay. Pretty equally distributed there with 3 and 5. All right, so let's start then with intermolecular forces. And this is a huge, massive list. And one of the things I find my students struggle with the most is just making sure that they understand that these words should not be something that causes them stress. Okay, so be sure that you keep in mind that an intermolecular force is a force that is between molecules, or even though it's kind of a misnomer, it can be between a molecule and an ion. And the name of the force tells you what two particles are involved in generating that force. So if you see the term ion dipole, what that tells me is that there is a force of attraction between an ion and a polar molecule. This would often take place in an ionic solution where you might have a sodium ion and then you might have a water molecule that has a partially negative end, and you're going to get a force of attraction between those two items. Anytime you see the word induced, induce means to cause to happen, kind of like if you induce labor, right? So when we have to induce a dipole, we're going to induce, it's going to be temporary. And so that means anytime we see the phrase induced dipole, that means the force that is, or the molecule that's involved is nonpolar, and we are generating a temporary dipole in that nonpolar molecule. So when you see two words, those are telling you, helping you figure out what two things are there. The only case where that is not necessarily happening is when you have forces between two nonpolar molecules. And then we would talk about this as being London dispersion forces, or in some cases, just dispersion forces. I did put a couple little asterisks there because I am missing one big popular and everyone's favorite intermolecular force. Please type in the chat what intermolecular force I have left off this list. Or you all can annotate the screen and that would kind of be anonymous. Ooh, there we go. Very good. Thank you so much. Hydrogen bonding. And that is about the world's worst name for an intermolecular force, because we generally think of a bond as happening within a molecule, not between. Bad nomenclature. So a polar molecule of a particular type can generate a hydrogen bond with a molecule of another particular type. So obviously the molecule involved has to include a hydrogen, but it can't be just any hydrogen. It needs to be a hydrogen that is highly, highly lacking in electrons from its own molecule. And as far as the AP curriculum goes, there are three atoms that when bonded to a hydrogen can cause that hydrogen to be very, 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 very partially positive. Type in the chat for me, what 3 atoms can potentially be bonded to hydrogen to generate a hydrogen that can hydrogen bond? Hi, evidently I have set the alarm off because I have the police here for a second. So Mr. A, would you like to pause the recording while I talk to the policeman? I shut the alarm off and it went green.
Yeah, it went off still.
Even though it was green?
I don't know other than.
There were other people, because it was green when I came in. It wasn't me. I've been here too long. It wasn't me.
Well,
Oh
that
my
was a
goodness.
first. Okay, if you're being held hostage, Alyssa, blink twice.
All good.
Yeah, Alyssa, I've got you on the intermolecular forces if we have to this morning. We're good. So keep,
Okay, thank you. This is a first.
Where were we? Oh yeah, the atoms to which a hydrogen should be bonded, I think. Are we on, Alyssa?
Yeah, they're looking. All right. So I see in the chat, yes, Ava, that is a nitrogen or an oxygen or a fluorine. And those 3 atoms have extremely high electronegativities. So they're going to pull electron density away from that hydrogen and then make this hydrogen need to form or find some electron density in an adjacent molecule. And in that adjacent molecule, you can find a lone pair of electrons, maybe. So we could have a intermolecular force that happens between a hydrogen atom that's partially positive and a fluorine atom in an adjacent, maybe hydrogen fluoride molecule, where we will get a strong force of attraction. Hey, I'm doing a review session.
Something to that alarm. So
Was it green when you came in?
yeah,
Did you touch it?
did I touch it?
Did you try to do something with it?
Oh, no,
Because it was green, it was unarmed because I was
It was
here.
armed and I put in the, so I don't know,
I wonder if it rearms itself after.
maybe.
I don't know, because I've been here since 9,
Oh,
so.
well, I did something.
See? All right. So I think one of the big issues that sometimes students have is when they explain things about hydrogen bonding, you need to be absolutely clear if you are writing that you are talking about a force between 2 molecules and not within a single one. And I think the best way to do that is to draw a picture illustrating what you're talking about. So that way, even if your vocabulary and your writing might not be 100% on topic, then the reader will be able to look at it and go, oh yeah, even though that right there clearly understand that it's between 2 molecules and not within a single one. That's the first biggest issue that I see kids have with identifying intermolecular forces and describing them. The second one I do, so the big thing that you do with intermolecular forces is you use it to determine the strength of attractions. It's to determine physical properties. And the most important thing I think is, because if I asked you guys to tell me which intermolecular force is the strongest, you all would tell me hydrogen bonding, because that generally is what we see, in terms of a list. Okay, a hydrogen bond. But you can't always assume that the general models and trends that we see are always true. So the most important thing I always tell my students is data trumps anything you know or anything you think you know. If they give you data and if you have data to interpret, whatever the data tells you is what you got to go with. So here's a question. At standard pressure, substance A has a boiling point of negative 85 degrees Celsius, while substance B has a boiling point of negative 34 degrees Celsius. Which substance has stronger forces between its molecules, A or B? Please add that in the chat. I got a B. Got an idea from anybody else? Now Kevin's like, oh my gosh, she's asking for another answer. Does that mean I was wrong? All right, the rest of us are not committing to a choice. So, okay, we get some more B's there. So negative 34 degrees Celsius is a higher temperature, right? Because it's closer to being a positive number. So if I have to heat something to a higher temperature to separate its molecules, then it must have stronger intermolecular forces. Right, so I want you to kind of keep in mind what we said here. Substance B has stronger intermolecular forces. Substance A is hydrogen chloride. Substance B is chlorine. And I put a state of matter on there. I get that depends on the temperature. But remember, substance B, you guys just told me, has stronger intermolecular forces. So here's what I would like my student participants to do. If you go up to the top of your shared screen, there's going to be a little button that lets you, there is going to be a little button at the top of that shared screen that is going to let you annotate. And I would like you to annotate, pick a text box and put your text box somewhere on this screen and tell me what intermolecular forces are present between chlorine molecules. Or you can type it in the chat. What intermolecular forces are present between chlorine molecules? What intermolecular forces are between all molecules? Yes, very good, Judy. So all molecules have London dispersion forces because all molecules have temporary electron cloud motion and electron cloud fluctuation. So anytime the question says, what intermolecular forces are present here? The question is, if the answer is London dispersion forces, and there might be an and. There might be an and. The next question you ask yourself is, well, okay, is this polar or is this not polar? Well, chlorine gas is not polar, so London dispersion forces is all we have. Hydrogen chloride gas, well, an HCl molecule, is that polar? Yeah, that's a polar molecule. So if one hydrogen chloride molecule is polar and the other hydrogen chloride molecule is polar, we would get dipole-dipole forces. And then you look at, well, do I have a NOF, an NO or F? No NOF, so I can't have hydrogen bonding. So if you have to explain why chlorine gas has a higher boiling point, it has a stronger intermolecular forces, you have to say, well, in this case, based on this data, these London dispersion forces must be greater than the combination of the London dispersion and dipole forces between the HCl molecules. And that's because of how many more electrons the chlorine molecule has. So please, if you're given data, you got to use the data, okay? You cannot use your idea to trump the data. If it's a multiple choice question and it says which of these is going to have the higher boiling point and it gives you a list of formulas, then you're going to go, well, is there hydrogen bonding? Because that's the strongest, right? Intermolecular force. But data trumps something that, a fact that we think we know. So I'd like to pause right here for a minute and ask you if you have any questions that you would like to ask me or your teachers or anybody else in this chat. All right. So sometimes you just got to know when to go on, right? So here is a question about the idea of solutions, which was the next thing that you guys, was the next most popular idea. So I would like you to read this question, please. And I've got a poll here. And you have 4 choices. So please don't pick E or F. That just makes me feel sad. But read this question and select your answer.
And there's a lot to this question. I think Ms. Clark would agree that you've got to know about the structure of calcium nitrate and maybe even write a chemical equation for the physical change that occurs when solid calcium nitrate is dissolved into an aqueous solution.
I think that is absolutely true. That is absolutely true.
And I think that's true of a lot of these questions. Is there's a lot of underlying understanding, and none of it, or very little of it, is memorization. So it really is much more to understanding. And what is the structure of calcium nitrate as a solid, and what's the structure of a solution of calcium nitrate?
Absolutely. Absolutely. So I would say the sole thing, Mr. A, that you would have to memorize, I guess, is that nitrate salts are soluble in water. Right. So if you have an ionic compound that has nitrate as an anion, it is going to be soluble in water. And when an ionic compound splits apart into its ions in water, the ions that make up calcium nitrate solid are a calcium ion and twice as many nitrate ions. So every time 1 unit of calcium nitrate splits apart into ions, we are going to make a calcium and 2 nitrates. So I'm going to end the polling. I'm going to relaunch the polling. Another shot at it there, my friends. So every time 1 calcium nitrate splits apart into water, and the change in calcium nitrate is -1, the change in calcium ion is going to be +1. We're going to get 1 calcium ion. And the change in nitrate ion is going to be 2, because we get twice as many nitrates as calciums, because 2 is twice as much as 1. And we have twice as many nitrates as calcium nitrates. So you have to kind of look at your coefficients there. And so the molarity of nitrate has to be twice as much as the molarity of calcium ion. So that kind of let us eliminate A and C. What do you see here about the change in calcium nitrate and the change in calcium ion? They're the same, aren't they?
Mm-hmm.
So I have an initial molarity. The label on calcium nitrate is 1 mole, it's 0.1 molar. If all 0.1 molar of that calcium nitrate splits apart into ions, I'm going to have 0.1 molar calcium ion. And so the answer to this question is actually D. And it is only, my friends, in the land of chemistry that you can have 0.1 plus 0.2 and have it equal 0.1. Right? And I know that's why you want to pick B, because that's what you guys have all picked, because you think like math, additive, it's got to add up to the 0.1. But you have to remember, what are we counting? Right? This 0.1 molar calcium nitrate says we're going to count the calcium nitrate as a group. What happens if we only count the calciums by itself? These guys are going to be equal. So the molarity of a solution that has only 1 ion per unit is going to be the same as the molarity that gets slapped on the label of the bottle. And the molarity of ions that have subscripts in their formulas are going to be more than the concentration that's slapped on the bottle. And so the molarity of an ion can't be less than the molarity of the compound on the label of the bottle. Right? If there's 1 in the formula, then there's going to be equal molarities.
Before you move on,
Please
Ms.
keep talking,
Clark,
Ms. Wright.
may I suggest, you've got a very nice diagram up there, but perhaps I could see the students being asked about the orientation of perhaps, or what that actually looks like in terms of water molecules, and also maybe to explain why, or predict whether calcium nitrate as a solid might be soluble in something like hexane, or I'm trying to think of another non-polar liquid, but hexane or cyclohexane.
I like that. I do like that. All right. So let's talk about that. Here's a water molecule around the calcium ion. We've got orientation A or orientation B. So you've got a choice of A or B. Which one correctly shows how the water molecule would orient itself around the calcium ion?
And how do you know?
And how do you know? Can't do that in a multiple choice poll.
No.
But, so let me remind you that in a water molecule, the oxygen is going to be the part that's a little negative, and the hydrogen part is going to be the part that's a little positive. And so do like charges attract, or do opposite charges attract? I'm going to relaunch that poll because not all of us got a chance to answer before I hit the button. So try your answer. Everybody put your answer in, please. Okay. So the calcium ion is positive. So therefore it is going to be attracted to the negative end of the water molecule and vice versa. So around the cation, you're going to have the oxygen part of the water molecules oriented. And around the anions or the negative ions, the water molecules will orient themselves so that the hydrogen can be attracted by the negative end of the negative part of the anion. I'm sorry, I'll be totally honest with you. I'm still a little bit bumfuzzled by the fact that the police were here earlier. So please just excuse me. I can't quite get it out of my head.
And there's a lot of underlying understanding, and students have to understand that when you draw something like this to represent not Mickey Mouse, but a water molecule, that you need to know that the water molecule is made up of an oxygen atom and 2 hydrogen atoms, that in fact it is bent, so it's not a linear molecule, and that there is the oxygen having a higher electronegativity will have a partial negative charge with a partial positive charge somewhere between the hydrogen atoms on the water molecule. So there's a lot that goes into describing a water molecule by that. And that's kind of the underlying knowledge that hopefully you've gained here.
I agree. I agree. And then Mr. A also brought up the excellent point. Well, what if you have a solvent that is non-polar, like hexane, for example, so C6H14. And we would have a long chain of carbon and hydrogen, a molecule of a long chain of carbon surrounded by hydrogens.
Oh, that's gonna have a lot of hydrogen bonding though, right?
Oh my gosh, there's all those hydrogens. It's got to have a lot of hydrogen bonding.
I'm kidding, students. Don't write that.
We are totally kidding, right? What's missing that makes this not have any hydrogen bonding? There is no oxygen, nitrogen, or, that's right, no NOF. Good job, Judy. There is no nitrogen, oxygen, or fluorine present. And can a hexane molecule hydrogen bond with water? Water has an oxygen. Could the hydrogen from the hexane molecule form a hydrogen bond with the oxygen in the water molecule? And the answer to that question is going to be no, because those hydrogens in the hexane molecule are not missing electron density. The carbon atom and the hydrogen atom have pretty similar electronegativities. The hydrogen atom that's bonded to carbon to, anthomorphize, they don't really have, it's happy with the amount of electron density that it's getting in that covalent bond with the carbon. It doesn't need to go out looking for electron density somewhere else. So not all hydrogens will form hydrogen bonds, only ones bonded to enough. And then it will make a hydrogen bond with enough. Now, if we think about why this calcium nitrate might or might not be soluble in hexane, one thing my students always want to say is, well, the hexane molecule, since it's nonpolar, it's not attracted to those ions. That's not true, right? All molecules and ions are going to experience some sorts of attractions for each other because you have random motion of electron clouds and regions of positives and negatives kind of everywhere. So that's not quite true. The idea, and I'm going to jump forward here a little bit because it still goes along with this idea. When we talk about solubility, we have three factors that are going to kind of govern whether something is soluble or not. We have attractions between the solute particles, which in the case of our example would be the strength of attractions between a calcium positive ion and a nitrate negative ion. We have strength of attractions between the two solvent particles, which would be London dispersion forces between a hexane molecule and another hexane molecule. And then we have, well, what kind of strength of attraction are we going to get between the solvent, a hexane, and the solute, a calcium ion or a nitrate ion? Because what we have to do is we have to break apart. It doesn't happen in a three-step process like this, but you have to, this is the way you can think of it. You have to separate or push apart the ions and break those attractions, which is going to add energy. You have to break apart, push apart the solvent attractions, which is going to add energy. And then when you form attractions between the solvent and solute molecules, then energy is going to be released, right? That's going to be an exothermic process. And I've drawn all three of these arrows size-wise as if they're equivalent, but they're not. Right? These, the calcium nitrate, these guys are strongly attracted together. The solvent, well, that's London dispersion forces, but that's a pretty big molecule. I mean, it's not ridiculously, there'll be some somewhat significant London dispersion forces. That's not going to be as strong as ionic bonding. So this might be a large arrow, and this might be a small arrow. And what kind of attraction or strength of attraction would we have between an ion and a nonpolar molecule? Well, that's going to be an ion-induced dipole force. that's not going to be a terribly strong force compared to an ionic bond. So the force of attraction that is able to form between the solvent and the solute has to be significant, equivalently significant at least, to the forces of attraction that the solute molecules are giving up and the solvent particles are giving up when that solution forms. So the attraction between a water molecule and an ion, which is a solute solvent attraction when you form an aqueous solution, is pretty strong. But the attraction between a nonpolar molecule and that ion is not terribly strong and is not enough to overcome the attractions that the two ions have for each other. Mr. A, you want to add in anything on that?
As long as we're talking about this, I think that that's an excellent description of solubility, but how about the role of, well, I hate the word ionic bonds and I prefer lattice energy. For example, if you had something like not strontium nitrate, would you expect that to have a higher or lower melting point? Let's see, strontium, yeah, okay.
So here we're talking about, we're going to kind of switch ideas a little bit here and think about the melting point of calcium ion nitrate solution scenario versus a strontium. We're going to pull these ions apart. We have to overcome the attraction between these ions. Which set would have to be heated to a higher temperature in order to allow those ions to move freely about one another, and why?
And I think the starting point here, Ms. Clark, is that students realize that dissolving and melting are really, we're talking about different processes. So there's no water involved. We're just heating this pure stuff up until it turns into a liquid. So what kind of forces are going to be overcome here?
So we would have to overcome forces of Coulombic attraction between these oppositely charged ions. What factors govern the force of attraction between charged particles? And that kind of takes us all the way back to the beginning of this idea, where pretty much I would say, well, 95% of chemistry can be explained by the idea that oppositely charged particles attract one another. This idea of Coulomb's law, that the force of attraction increases with the magnitude of the charge on the particles, and the force of attraction decreases with the distance between the point charges of the particles. So if I were to compare these two factors, the magnitude of the charges are the same. The nitrate ions are both negative. The calcium ion is a +2 and the strontium ion is a +2. So the magnitude of charge is the same. What's going to be different is the distance between the point charges. And so if we think about on the periodic table, calcium is closer to the top, strontium is farther to the bottom, which means strontium has more energy levels containing electrons. And so it's going to be a larger in volume ion. And so the distance between that point charge, if you think of point charge as like the center, imagining the center, and the center of the point charge of the nitrate is going to be more. So as distance goes up, force of attraction goes down. So you wouldn't have to heat that as high to melt it. We're going to come back and talk about that one here near the end. So the last thing in this idea that you all wanted to make sure we talked about was the idea of the Beers-Lambert's law. So Beers-Lambert's law is going to be a lab situation where you are going to have solutions of different intensities of color. And we can visually look at like Kool-Aid and say, oh, that Kool-Aid is concentrated and that Kool-Aid is dilute and that Kool-Aid is really super dilute. It is like barely purple at all. So we can kind of do Beer's law qualitatively with our eyes. How concentrated is the solution? We can also measure that with a spectrophotometer. And there's a direct relationship between the concentration of a solution and how much light that solution will absorb, or how intensely colored that solution is going to appear to be. So we have this direct proportional relationship, and this allows us to measure the absorbance of an unknown solution and then say, okay, if it was, let's say 0.6, I can use some ACT skills there and say, okay, well, the concentration of that solution then is 0.3 molar. Because molarity is not something that we have an instrument we can measure. We have to measure it we have to measure a different property and then convert it. So Beer's law is given on your AP Chem equation sheet. Here is A, that's on your y-axis. Here is C for concentration, that's on your x-axis. A is called the molar absorptivity constant, and this is specific to the substance that you're studying. What color is it particularly exactly? How well does it absorb light? B is the path length that we allow the light to travel through the substance. So here's an example of the cuvette that you would use to do your Beer's law experiment. All right, we're going to shine light on that substance. A certain amount of light is going to come out, and a lesser amount is going to come out, and we're going to get a ratio. The higher this concentration is, the more of this light gets absorbed and the less comes out. So you want to make sure, if you think about when you shine light on a substance, if you were to shine all wavelengths of light on a substance, one of those wavelengths is going to do a much better job of being absorbed by the molecules in that solution than others. And so one of the factors that it is important to consider when you're looking at choosing a particular wavelength of light, well, it's actually the important one, is what is the wavelength of maximum absorbance? You want to make sure that you are using the wavelength of maximum absorbance for the substance that you are trying to study, because that way you are going to get the best differentiation in results. So there's one variable you have to consider. Here is your path length, right? That's your other thing that has to be maintained, because if you were, for example, to, let's say, double that path length, well, now you have twice as many molecules that light has to pass through and has the potential to be absorbed by. And so as you increase your path length, you're going to increase your absorbance as well. So that's a variable that has to be held constant. There are two main kind of experimental errors I can think of that come along with Beer's law. One is that you have touched the outside of the cuvette and you have failed to wipe that off. And in that case, you are going to, the oils and things in your hands are going to scatter the light. And so you are going to get a falsely high absorbance here. It's going to absorb more light than it seems like it should, because not all of the light has been able to pass through the solution. It's been bumped around by the oils. The other thing, and this is an error in spectroscopy, it's an error in titrations, it's an error in a lot of things. When you're going to use an instrument and make very careful volume measurements, you always need to make sure that you rinse whatever container you are using with the solution you're going to test after you've rinsed it with distilled water. because if you don't do that, you're going to leave little droplets of distilled water in your cuvette or your burette. And when you add your solution, it's going to be diluted by that water. And so if you don't rinse with your solution, you're going to get a falsely low concentrate, absorbance and then concentration. Anybody want to ask any questions about Beer's law? Nope. All right, Mr. A, you want to add anything about Beer's law?
No, I think that covers it. Maybe you can show a sample. Do you have a sample question handy? Or?
I did not have a sample question handy of this because I'm a bum on this one.
That's okay. Hopefully most of our students.
Ms. Clark, fortunately, I'll have something similar to deal with this in our next presentation. So it piggybacks really well with what you're doing right now. So I've got some data that we can look at in a bit.
Excellent. Excellent. Thank you so much, Ms. Price. I do, however, have some questions about some other ideas that we will use our remaining time here to discuss. So one of the topics that is included is being able to understand this graph about bond formation. So I'm going to pop open a poll here and ask you, what's the approximate, so let's talk about this graph a little bit before you have to give an answer. How about that, since I'm supposed to be teaching you too, or reviewing with you. So this graph is somewhat odd compared to other graphs in that it is often read from right to left. So we have the potential energy of a system based on how far apart the two nuclei are. So we have two atoms and they're changing distance apart from one another. So if they are very, very, very far apart, their potential energy is assigned a value of 0. As they approach one another, the nucleus of one can begin to exert an attractive force on the electron cloud of the other, and vice versa. And the potential energy of that system goes down to a minimum. If they continue to get pushed closer together, then the like charges of the nuclei can begin to exert repulsive forces on one another, and the potential energy of that system can go back up. So no interaction at 0. Attractive forces as the potential energy goes down. Repulsive forces dominate or begin to become more significant as the potential energy goes back up. So knowing that information and knowing that bond energy is the energy that is required to separate bonded atoms. Which of those 4 choices would describe the bond energy shown in this diagram?
And I'm sad to say,
I
Ms.
like
Clark,
the, go ahead, Mr. A.
I'm sad to say that my campaign to call it a bond dissociation energy has gotten absolutely 0 traction, because that still confuses me when you talk about bond energy and as the energy to break the bond, whereas calling it a bond dissociation energy makes it a little bit more explicit. But,
Ooh, I would like that term. I can buy into that. So, you know, just because it's not in all the textbooks and everything doesn't mean that we can't add that in there. I do that with my kids all the time. They call it this, we're going to call it that. Bond dissociation energy is going to tell us that the energy required when we're going to dissociate, pull atoms apart and break bonds, it has to be a positive value. So that's what lets me eliminate A as a choice. And several of you chose A, and I think that is awesome because you are reading it off this graph right here, right? This is the potential energy of the system when it is bonded. If we are going to break that bond, that means that we're going to pull those atoms apart so that they don't interact with each other anymore. We are going to raise their potential energy to 0. So the bond energy is the positive value of that dip, not the negative one. And I agree with Mr. A, it's wonky. I don't like it. But the idea is this is the energy of the system when they're bonded together. How much energy are we going to put in to pull those atoms apart? And so the answer we would have picked is D. One thing you also might be asked to do with this curve is, let's say this represents the bond for the curve for 2 fluorine atoms. How about if we were to graph on this axis the curve for 2 iodine atoms instead? How would the curve differ? This is for 2 fluorines, which if you think about on the periodic table, fluorine has 2 energy levels containing electrons, versus what if we were to make it for iodine, where iodine has 5 energy levels containing electrons. What's going to happen to the internuclear distance when the 2 fluorines are able to overlap versus when the 2 iodines are able to overlap? Do you think the bond, the distance between the 2 nuclei is going to get bigger or smaller? We don't have a lot of confidence about this one. That's all right. No worries. So as the atoms get larger, their outermost energy levels, which is where bonding occurs when those overlap, are going to be farther from the nucleus. And so the distance between the 2 bonded nuclei is going to be greater. And so therefore this peak or this minimum is going to shift to the right because bigger atoms are going to have longer bonds. If the atoms are farther apart, remember our idea with force of attraction or energy and Coulomb's law, as the distance between gets larger, the force of attraction gets less. So the amount of energy required to break that bond is going to be less. And so the minimum is going to be closer to 0 because that bond is not going to require as much energy to break. And so the minimum is going to shift to the right and up.
And Ms. Clark, I'm glad that in the questions you talk about the way the shift of the minimum point of the graph, but because the whole graph is not going to shift. And it's important that students realize that no matter what bond at large internuclear distances, the potential energy is set to 0. And that, so it's always going to have this general shape. So for iodine, you're not going to shift the whole graph up. I'm not doing a great job with my trackball trying to sketch this for you, but
oh, you're doing it. There we go. Okay, yes, thank you.
Look a little bit like that. So it will not. Let me pick a color here that says not. It will not do something like this and go above that line.
It's an excellent point. Yes, that will always stay right at that, right below that minimum of a 0 value.
And that's just the way we talk about energy. That's just the way we talk about energy.
Yes. The other thing I would suggest is this point is never going to go up and to the left, right? It's either going to go to the right and up, or the minimum is going to go to the left and down. Either the bond gets shorter and requires more energy to break, or the bond gets longer and requires less energy to break. So even though I put 4 choices here for a multiple choice question, really and truly, the only possible choices are A and C. Minimum goes right and up or left and down. Let's try one more. Suppose this curve represented a single bond between 2 carbon atoms. How would the curve shift to represent a double bond between 2 carbon atoms? So now we're going to have more the amount of charge that is present between those 2 nuclei to allow the force of attraction is going to go up, because now I have more negative charge for those positive nuclei to be attracted to. So what's going to happen to the bond if I have more force of attraction, shorter or longer, is the way I like to start thinking about it. And remember, I didn't change the order of the answers here. Really, you can only pick between B and C. The bond is going to get longer and weaker or require less energy, or it's going to get shorter and stronger. Okay. My students, and Mr. A, I would love some help on how to explain this better so they don't get confused. My kids think that there are more electrons in between the bonded nuclei, so you're going to have electron-electron repulsion is going to get greater, and that's going to be, so now they can't get as close together, which actually my friends here on this today, that is wrong, right? You're going to get a shorter bond and a stronger bond. C is the right answer here. Help me fix my life, Mr. A.
Yeah, I mean, it's hard because they are true that electrons do repel each other, but they're attracted to those nuclei, and those electrons are really the glue that's pulling those nuclei together. And it's not that the electrons are attracted to each other; they still repel each other, but boy, they are sucking into those 6 proton nuclei, and that's what's doing. And that's kind of the same reason that many students seem to think that the electrons will attract each other in the 1s orbital of a helium atom, but they're not. They only go into that 1s orbital grudgingly because they are so attracted to that nucleus. So this even comes up with atomic structure. And this is the idea for students, and I hope you'll find this useful in science, that really AP chemistry, it sounds like a hard course. It is a hard course, but it's not hard because you've got to memorize a lot of stuff. It's hard because you have to build models and interpret those models. And it actually gets easier when I think you start doing that. So, and there's a lot of underlying knowledge that goes into realizing that these lines represent electrons and these letters represent nuclei and how many protons are in that nuclei, and that electrons have a negative charge and protons have a positive charge, and that they are opposite charges attract. So, I mean, before we even start talking about this question, there's a lot that you've got to understand. But the idea that okay, these electrons are really gluing or pulling these nuclei together, and it's the attraction of the nuclei to the electrons that is causing this bonding and the decrease in energy, rather than any effect between the electrons, which is still there, but we kind of it's minimal, and we kind of have to ignore it. And I mean, it's not easy to understand, but it comes with practice and with thinking, which is the hard part, at least hard for me.
I think I can use that idea of, yes, the electrons, those 2 additional electrons do repel each other, but they're also experiencing the force of attraction of a much greater amount of positive charge because of the more protons in the nucleus. I can sell that. Thank you.
I think, Ms. Clark, too, one thing you can add that a lot of my students have difficulty with is the fact they forget that the nucleus has more than one proton. Because if you think about it, we write carbon, we write nitrogen, you know, we look at it as one symbol. And as a consequence of that, we get this idea, one symbol, one thing. We forget that carbon has 6 protons and nitrogen, and so on and so forth. So when we start thinking about the numbers of protons in between those atoms, we can think about, hey, that's a charge of, +6 attracting an electron is a charge to +1 versus -1. And so that repulsion you're really getting is kind of mono-y-mono between the electrons. But the attraction you're getting are multiple protons, or the attraction of +6 of a nucleus to 1 electron from right there too. That's something else that helps my students as well.
And in fact, I would say that the 6 protons is the defining property of a carbon atom. And I always tell my folks that, well, we chemists, we have a funny way of counting. Instead of saying 1, 2, 3, 4, we say hydrogen, helium, lithium, beryllium, boron. Because that's all you need to know is how many protons are in the nucleus. And that is code. If you can apply a little bit of imagination and then a little bit of understanding electrons to telling you everything you need to know about that particular element's atoms.
All right.
This is probably a good time to take a short 5-minute break. I'm going to pause the recording and give folks a chance to get something to drink or maybe use the restroom, and we will pick this up in about 5 minutes with some chemical kinetics. So thank you so much. I'll see you in a little bit.
Thank you.
So welcome back.
Well, good evening.
And
yes, good morning, students and faculty who are right here too. It's always great to be with you guys. I wish we could do it more in person than we are from right there. For those new, I'm Mr. Price. I teach AP Chemistry at Trinity Valley School, which is a private school in Fort Worth, Texas. I've taught AP Chemistry now. This is like my 23rd year of teaching AP Chem. And I know known Mr. A for a long time because we both work at the AP reading together. And we have a really good time there, particularly when we get together. So I was really honored and happy when he asked me to come along and talk to you guys a little bit about chemical kinetics. And kinetics is kind of one of those topics that, when most of your teachers do it, and I hope our teachers will agree with me, we have a tendency to kind of do it in one fell swoop. And it's maybe 2 weeks or 2.5 weeks of kinetics that we work on. And sometimes you really get it and other times you really don't. And the problem with kinetics is you go through that unit, and after you go through that unit, you may not see it for a long time. So you guys may have done kinetics really recently, or like my students, I do a lot of kinetics in the fall. So it's been a long time since my students have seen some kinetics. And so what we're going to do today for kinetics is we're going to take one problem, and your teacher's going to have access to this problem, and you're going to have access to this problem. And we're going to work through this one problem in great detail, which is really going to talk us through all the major aspects of kinetics. And hopefully it'll show you kind of all the things we need to think about from right there. It'll cover most of the kinetics unit. We'll miss some stuff on catalysis and we'll miss some stuff on potential energy diagrams, but we're going to run through the unit itself. And I'm going to kind of show you, let me share my screen and show you what you're going to get. And particularly for teachers, I think Mr. A put up a file on the website. I'm going to show you right here too. And there's going to be 2 versions of the file. There's a student file. Let me share my screen. Hold on one sec. So hopefully everybody can see that now. There's a student file, and then there's going to be a kind of the file that goes with what we're talking about. And the student file is the first 2 pages of what you see right here. So this particular document that you see right there, these first 2 pages are what we're going to be working with a lot today. So I'm going to have to, of course, move back and forth as we go through. But on the website for the files itself, there's a copy of this. And there'll also be a blank copy of everything we're going to do today. So if you want to go back and use this, for example, teachers, if you want to use this with other students moving forward, feel free to from right there too. And this is a problem that I wrote. It's from a lab manual that myself and 2 of my friends who teach chemistry, or actually one's retired, but one who teaches chemistry in Florida and the other one in Ohio, Dr. Bernstein and Mr. Bracken and I wrote this in a particular for a lab manual. We're going to actually kind of work through this problem today because it's a problem that kind of combines everything we deal with, and we call it the mechanism mystery. So instead of reading through that kind of goes through here, what I want to kind of show you is what the problem deals with. And I was appreciative of Ms. Clark because she was kind enough to talk a little bit about Beer's law. And so what we want to talk about here is we want to talk about the reaction of food coloring and bleach. And so to kind of get us let off from right here too, I'm going to show you what the reaction looks like. And I'm just going to pick a run from right there. And hopefully everyone can see my screen and see the video. And I kind of want to give you a heads up of what happens here. And our teachers back who visited us in the fall for our discussion of Beer's Law back in the fall, you might recognize these videos. I thought it'd be good to use the same sort of thing again because you guys already have access to this. So what we have here is when I did this, and this was really for at home use, I've got two different types of Gatorade. I've got Glacier Freeze on the left, and on the right, I've got Cool Blue. So if you go down to 7-Eleven or somewhere, you can grab those two. And those are just the Gatorade stock solutions. Those are just the solutions of Gatorade. I just pour them in 2 cups from right there. And in the middle, I've got some bleach. Okay, and that's just bleach. And the way I made that bleach is I took just a bottle of bleach, all right, and then from that bottle, I took 30 mils of the bleach, and we'll talk about what bleach is in a second, and I added it to water so that the final volume was 100 mils. So I diluted the bleach a little bit from right there, okay, as well. And then all I did is I put a drop of food coloring that I got from the store, blue food coloring, into the bleach. And I want to show you what happens when I do that. Okay, so I'm just going to go right in there. So you'll see me. I'll put a drop of blue food coloring into the bleach, and I'll start a timer when I do that. So let that happen real fast. Okay, and I mix it up to get everything going from here. And you can do this at home. It's really easy to do at home too. I did this with just a little camera here and then that. All right, and if you watch, you'll see very quickly that the blue food coloring starts to fade, and you can see it fading from right there. And in 30 mils of bleach, it actually fades pretty quickly. And in the interest of, well, actually, this one's pretty quick enough, we can probably watch it in real time. And you can actually see it fade and fade and fade. And then eventually what will happen is that the color will go back to the original solution of the bleach. Okay, it takes about 50 seconds if I remember this run, maybe a little bit less. I'm going to fast forward here for the interest of time. So you can see by about, a minute in, we're about done because here's the original color. Here's the color at about a minute, okay, from right there too. So it completely reacts, okay? Now, this is important, just a kind of a more general chemistry thing, is that just as a little bit of review, bleach is actually sodium hypochlorite. It's NaOCl in water. So it's a solution of sodium hypochlorite. And what makes bleach so interesting deals with the redox properties, the oxidation reduction properties of bleach. So if we look at OCl just for the sake of discussion, the sodium is a spectator. It doesn't do anything. We could use potassium hypochlorite or calcium hypochlorite. It's really the OCl minus ion that's the important guy here. What's interesting is the redox chemistry of the bleach deals with the oxidation number. And just as a quick little review from a side here, what makes bleach really interesting is if you remember how we assign oxidation numbers, okay, typically, oxygen's always going to take an oxidation number here of -2. And it does that in every compound except with fluorine. Well, chlorine, which typically is a halogen, takes an oxidation number of -1. In bleach, it has this interesting oxidation number of +1. And that +1 oxidation number puts an atom, which really likes electrons like chlorine, in kind of this weird oxidation state. And that's what really drives bleach's chemistry. What the bleach is trying to do is to get electrons to that chlorine, which matches very well with some of the stuff that Ms. Clark was talking about earlier. And so pretty much all the chemistry of bleach is this poor chlorine that doesn't have a lot of electrons, is trying to draw electrons to it. And where it's getting electrons from is it's actually getting electrons from the food coloring. So the chlorine is stealing electrons away from the food coloring, which then decolorizes the food color. Okay, it's kind of an aside. The chemistry here is really complicated. So the way we're going to represent it today, just as simple as possible, is all we're going to say is that we have food coloring, which I'm going to label as BFC, blue food coloring, plus just the OCl minus, which is the bleach, that's the other spectator, goes to stuff. I don't know what stuff is, nor do I really care, okay? The only thing I know is that the stuff is colorless. And of course, the blue food coloring has color, and the bleach has that kind of yellowish color, the solution from right there, okay? So here's the thing is I want us to think about real fast and to kind of put from right there too. And if you guys, as students in particular, if you could type some stuff in the chat that I'm watching from right here, my question for you is from what you've learned in class, could you tell me some ways or some factors that would make the color go away faster? So if I wanted to run this experiment and make the blue food coloring go away super fast, what are some of the things you might do in this experiment to make that happen? So students, if you would type that in the chat from right there, just some thoughts that you would have, okay? We'll give everyone about 30 seconds to go from right there too before we start reading on top of that. I see a really good one to start from right there. Okay. And we'll give a couple more seconds for right there too. If anyone wants to type anything else in. All right, so I see higher bleach concentration, and that's exactly right. One of the things you could do is you could up the concentration of the bleach. Now, the real question for that is, why would a higher concentration of bleach do anything? Well, let's talk about that real fast. I'm going to move a couple pages down the line, okay? So on a molecular level, if we're talking about the reaction of blue food coloring plus bleach to make stuff, which I'm just going to call products, all right? On a molecular level, when we watch a chemical reaction, what has to happen for two things to react, okay? So we got the one with the higher bleach concentration. Take another second if you want to put in the window, why would a higher bleach concentration make the reaction happen faster? In a sentence or in a quick statement, what would you say? Why would a higher bleach concentration make the reaction happen faster? Does anyone want to comment on that as well? So think about if you need the two things to make product, what do they have to do? Anyone want to add anything to that real fast? Okay. So therefore, what we've got to think about for things to happen from right here is there are actually three things that have to happen for substances to react. One, they have to collide. They have to hit. And we'll see that on a molecular level in a bit. So the more they collide, the better chance a chemical reaction has to happen. And right away, that's where the concentration's coming into play, because the concentration means there are more particles in a box. And if we have more particles in a box, so for example, let's say there's one box, and here's a second box. And if this box only has two particles in it, and they have to collide, and this box, let's say, has 6 particles in it, the chances of collisions between the 0, the O's, and the X's would be much greater in this box than it would be in this particular box. So the more collisions we have, the better they would be. A higher temperature would make it disappear faster as well. That's exactly right, because the collision has to satisfy some properties. Not only do they have to collide the right way, and they have to collide with enough energy. So if I increase the temperature, I'll make the reactants move faster. Well, if they move faster, they're going to collide more often. And not only that, the more often they collide, a percentage of those collisions will be correct in the right orientation to get things to go. And you need to collide with enough oomph to start breaking bonds and start the chemical bonding process from right there too, as you break some bonds and then make new bonds. So really, you've got to collide. Those collisions have to be the right way, and they have to have enough energy, okay? So that's what's going on a molecular level. The problem is the only thing we see, okay, the only variables that we can impact to affect that really is one, we can change the concentration, we can change the temperature. Those are the two biggest things that we can do in a given experiment to impact those things on the molecular level. Because if we increase the concentration again, there'll be more collisions. So if there are more collisions, there'll be more that go the right way. And we're giving more molecules that have more kinetic energy the opportunity to interact. And if we increase the temperature, there'll also be more collisions because they're moving faster. Obviously, if there are more collisions, there'll be more with the right way to do it. And at a higher temperature, you have a higher fraction of molecules that actually have enough energy to interact as well. So these are the two experimental variables we can mess with. But this is what they're dealing with themselves on a molecular level, okay? So with that in mind, whenever we're dealing with kinetics, there are two things we really have to think about, okay? One thing we have to think about is how do we measure the kinetics? Like how do we describe it? And then two, what we want to do is that how do the collisions, how do the molecular level events impact what we measure? So the first thing we typically deal with when we're working with kinetics in the lab is how do I actually make a quantitative definition or quantitative description of just saying, oh, increasing the concentration, it will increase the rate. Is there a way to make that more mathematical? And the answer is yes. And the way we're going to look at that is to go back and look at the rate law, okay? So let's go back for a second. And here's our reaction. Blue food coloring plus OCl minus goes to products. And the question I have based as a review, well, what is a rate law? And how would we write a rate law for this particular problem? Okay, from right there too. So if we think back for a second for an aspect of a rate law, remember what a rate law is doing is that the rate law itself is a mathematical expression that relates the concentrations of the reactants and the reactants to how fast the reaction happens. And the biggest problem and thing that we forget sometimes with rate laws is when we write one down, what we're going to say is that the rate law is directly proportional to the concentration of each reactant raised to a power. So we have two reactants in this rate law. We have BF, blue food coloring, and OCl minus, and those raised to a power, all right, tell us what the rate is itself from right there too. Now, one of the biggest mistakes that we see students make is that they believe that they can derive these powers directly from the balanced chemical equation. And that's not true. These powers, which you may remember are called orders, okay, these exponents, can't be discovered just by looking at the balanced chemical equation. And we're going to see why that's true today as we go through review. Okay, on top of that, the only way we can get these orders is actually by doing the experiment, which is what we're about to do. Okay, so what we can do is that we need to come up with a way to mathematically determine these orders. Now, notice I said directly proportional to, and you may or may not be familiar with using this little symbol. It's the Greek letter alpha, all right, that means proportional to. And one of the things you learn a lot from your gas laws is that there's always a way to turn a proportionality into an equation. And the way we can always turn a proportionality into an equation is by adding a constant. So if I want to get an equality here, I can say, hey, that's going to be a K, some constant, times blue food coloring times OCl, and each is raised to a power. This constant is called the rate constant. And the rate constant is where all your temperature dependence is. All your temperature stuff is thrown into the rate constant, okay? All your concentration data is thrown into the orders. So A and B will let you know how changing the concentration of the reactants impacts the rate of the reaction. And K basically will only change if I change the temperature. So for today, for what we're gonna do everything at one temperature. So for us, we're not gonna mess with the value of K. But if I were to change the temperature, increase the temperature, K would go up. If I were to decrease the temperature, K would go down. So K is our quantitative way of measuring how much temperature impacts the rate of the reaction, okay, from right there too. Now, the first thing we want to deal with is how do we get this A and this B? That's the first important thing that we typically do with data, okay, from right there too. And one of the things that becomes really important if you look at a lot of chemical reactions that we deal with in AP chemistry, particularly a lot of questions and problems, I want to move this little thing out of the way from right here because it's right over my part, which you can't see, is that a lot of reactions you'll see look something like this. And these are most problems that we see a lot on an AP chemistry exam. Some reactant A goes to products. And then the last will write the rate law. Well, the rate law would just be the constant, the rate constant, raised to A to a certain power. And a lot of our questions deal with how do we deal with figuring out what little a, what the order is. Well, one of the little problems that pops up is that these reactions are really easy to study mathematically, but they're almost impossible to do in the lab. Very rarely do we find a reaction in the lab where we have one reactant that goes apart to products. And the reason why this is a big problem is that when one of the ways that we can study a chemical reaction is to watch the concentration of A as a function of time. So what I want to do is I really want to watch how A changes as a function of time. And so A could do a lot of things. It could go like this, it could go like this, okay? It could go down like so. There are a lot of different ways that A could change as a function of time. But what we really want to do when we study this graphical method is that we only want to look at the result of A. And the problem back here is when we have a reaction like this, we have two reactants, and the rate actually depends on the concentrations of both. So one of the things we frequently have to do when we have multiple reactants is that we isolate one from the other, okay? And the biggest way that we typically isolate one from the other is that we make the concentrations of the reactants really different. And what I want to show you from an aspect of the video to kind of talk about that really fast is I just want to show you two runs from right here. Here we go. Is that 30 trial one? Yeah. Here's the same run done again. And so I'm going to run the same reaction twice in both videos. So this is the same run, the same trial. And what I want to show you is watch the time. So if I watch the time from right here on the first one, I put the bleach in, and notice it completely goes away in about 50 seconds, all right? In the second run, I use the exact same container of bleach, okay? Exact same container of bleach, and I put it back in, so I'm just running it again. And notice it went away again in about 50 seconds. It took the same amount of time. Well, that's important to know because what that's telling me is between my runs, my concentration of bleach hasn't changed. Because if the concentration of bleach between the first trial and the second trial, it changed a lot, the second trial would have taken a lot longer to finish because the rate depends on both of them. So one of the things we typically do, and you may see this in data, is we make the concentrations of one of these reactants right here, we make the concentration of this really big, and we make the concentration of this really small, so I can watch how the food coloring itself changes without worrying about changing the concentration of the bleach, okay? And there's a name for that. We call that a pseudo first order reaction. We're not gonna go that in great detail from right here too, but it's a way we separate one reaction from another reaction so we can just study one versus the other. So the take-home message that we do for you in AP chemistry typically is that when we're looking at multiple reactants, we'll make the concentrations wildly different so that changing one doesn't necessarily, that one is so much larger than the other that during one trial, that one won't change. And so for the rate won't be affected by that. So this experiment right away lets me just look at how the food coloring is affecting the rate. So I can just watch the food coloring across the board and how it changes tells me if I could get information about it, it would give me information about what the rate is with respect to food coloring, okay? Yeah, that's exactly right. It'd be swamping the reaction. That's exactly correct, okay? Now, I can't do it with the data I have right here, but this goes exactly to what Ms. Clark was talking about, is how could we actually measure the concentration of the food coloring as a function of time if we wanted to. And this is where we would need a spectrophotometer like Ms. Clark was talking about, and we would use Beers' law. And what we would do is we would put that blue food color in a spectrophotometer. So I would just take a little cuvette, I would start the reaction right here, take this solution, pour it into my cuvette. So here's my nice little blue solution. And then light would pass through as the reaction was occurring, and my cuvette would then allow me to see the concentration decay. And I could actually get a number for this, which would be the absorbance from right there. Well, one of the things I've done for us is I have that data for us. So I don't have a special spectrophotometer for us right now, but I grabbed some data for us for that. And so here's the data for a bleach run. So what this is it shows the absorbance of the bleach. So more absorbance means more blue as the run goes. And again, this is only focusing on the blue food coloring. So when I look at the rate law, which again, I'm gonna write, is K times bleach times blue food coloring. I don't need to worry about the bleach right now. Its concentration is constant during all of this, okay? So as a consequence of that, we're only focusing on the blue food coloring. So my question for you is, how can I figure out the value of B based upon this data, which is something we see all the time on the AP chemistry exam. So what can I do to figure out that value of B based upon the data? What graphical techniques could I use? So very quickly in the chat again, and I want you to think back to what you've done some parts of this year. Do you remember how you would manipulate this data in order to try and figure out what the order with respect to food coloring is? So any thoughts whatsoever that any of our students would like to talk about? And again, this may have been covered a long time ago to kind of deal with that, okay? And this is actually real data, so we're gonna play with it here in just a second, okay? All right, so what we do in this particular case is we're going to use a graphical technique, and I'm not going to go into derivations of the graphs. That's something that you can look up in your textbook or your teachers can talk with you about in review. But there are three things we typically want to plot, because it turns out that there's a direct relationship between the order and what type of graph will give us information. So typically the orders, which again are the exponents right here, are integers. They don't always have to be integers. But in our AP chemistry world, we kind of like to keep them in integers. So what we could have is a zeroth order reaction where the exponent here is 0, a first order reaction where it's 1, or a second order reaction when it's 2. And we can deduce those orders from the rate laws themselves by looking at specific graphs. And it turns out that if we graph just the concentration of the food coloring versus time, if that graph were linear, then the order is zeroth order. And again, the derivation of that is something you probably talked about in your classes from right there, and not something we're gonna have a lot of time to get into today, but it's across the board and you could go back and review that, all right, from right there. So what I wanna do real fast is let's graph this data and actually see if the concentration versus time is linear. So in order to graph that real fast, I've actually already created some data over here, and I wanna show that to you on the graph. So let me pull up, and there's a really cool website called InPlot. And InPlot, and I've given the link, it was in the data teachers that was from last night. And I really like this because it's cheap and easy way to graph. And you can just copy and paste data over from Excel or Logger Pro or whatever else you want to use from right there too. And so what we're seeing right here, I just copied and pasted the same data which is on the table. So the x-axis is time, okay? And the units there are seconds. And the y-axis is absorbance. So what's what Ms. Clark was talking about, what the spectrophotometer measures. And absorbance doesn't have any units. And so we look right now, if we graph the concentration versus time, it's clearly not linear. So because of it not being linear, that means that this reaction is not a zeroth order reaction, okay, with respect to blue food color. Okay, great. But the only way I can tell that is to actually look at the data and say, oh, it's curved. So therefore it's not zeroth order. Well, what can we do if it's not zeroth order? Well, we can look at some other aspects of data. And the second we can look at is if the reaction is first order, what we're going to graph at that point in time is not the concentration. We're going to graph the natural log of the concentration of food coloring versus time. And again, mathematically, we can prove that if this exponent is 1, then this graph of natural log of concentration versus time will be linear. And for second order, what we could do is if we plot 1 over the concentration versus time, that graph will be linear if it's second order. So let's quickly graph the natural log, and I'm gonna go right over here. I need 1 second because I gotta create the natural log. So give me 1 second because I'm doing it actually in real time on my computer and getting the data. So let me cut and paste that. There we go. And I'm also going to do 1 over the concentration too, just to show you something. Equals 1 divided by that. And again, a spreadsheet or your calculator is good. And typically when we do this on the AP exam, we give you this data because we don't want you to waste tons of time actually having to drive all this data across. Because if you make one little calculation mistake, it of course can cause a problem. So let me go back here to sheet 2 and let me re-grab the times. So here come the times back. Oops, there we go. And here comes the natural log data. And again, I just use my calculator to take the natural log. So there it is. And you can see both plots from right there. And so right here, up top, it's scaled weirdly, but there's the curve from we see from before. And now we're starting to see the natural log data. And the natural log data across the board starts to see right away that now we're dealing with natural log of absorbance. So I'll put that in right here because we're putting everything on the same graph. There we go. All right. On the natural log data, it looks like it might be linear. And so one of the things I'm going to do real quick is do a curve fit. Okay. And if we see the fit right there, that looks really, really, really good. And the parameters of the fit that we could talk about, we could pull the rate constant out of the fit if we wanted to, but I'm not going to deal with that today. I don't really care about what the value of the order is, but the fact that the natural log graph is giving us a straight line is indication that, hey, we've got a first order reaction. Now, just out of the fun of it, let's go ahead and look at very quickly, the second order plot, just to show it to you on the same graph. So again, I'm just going to type in the times here. And I'm going to type in the 1 over concentration data. And if you look clearly, notice how curved this is. It just goes up through the roof. And so with my really poor drawing skills. And so therefore, we see right away it can't be second order. So this data right here, it's clearly first order data. So one of the ways that we're typically going to examine you to tell if you can look at from data of concentration versus time that we're going to examine you is we're going to have you look at graphs. And if the data is 0th order, a graph of concentration versus time will be linear. If it's first order, a graph of natural log of concentration versus time will be linear. And if it's second order, a graph of 1 over concentration versus time will be linear. But the only way you can do that is to actually do the experiment. So we see right now that the little exponent b with respect to blue food coloring, b here must be 1, okay, on top of that. And again, it was important that we left the bleach alone, okay, from right there too. It's important to only let the concentration of the bleach stay constant in order to deal with that, because otherwise, if both of them are changing significantly, we can't just look at these graphs across the board. So when you look at data a lot, you're going to see that the concentration of one of the reactants is really small and the concentration of the other reactant is really large, okay, from right there. So the question becomes then, how do we get the rate with respect to bleach? Because we can't, the problem is that, well, the biggest problem is that there's no color involved. Because if we go back and look at the data, if we go back and look at one of the runs, unlike blue food coloring, which obviously changes color, the bleach itself doesn't do much for me. So if I look, I start with colorless, okay? And if I'm watching this, what I'm watching right now is I'm just watching the blue food color go away, okay? So is there a way to tease out what's going on if I change the concentration of the bleach? And the answer is actually yes. And in order to do that, I want to show you 2 different runs, and let me move this one over, with different amounts of bleach, okay, from right here. So let me just explain what the difference is in both cases. On the run up top, what I did was I took 10 mils of bleach and I diluted it to 100 mils. On the run on the bottom, I took 20 mils of bleach and I diluted it to 100 mils, okay? And then I ran the reaction each time. And again, in the interest of time, all right, I am not going to run the whole reaction across, but what I really like you to watch is watch right there. Watch this solution, this cool blue, okay, on top of that. And what I really want to watch is after I add the food coloring, when does my food coloring solution equal the cool blue solution about in color? So if I go with the first run with the bleach, with the 10 mils, I run it and you see it gets cooler and cooler and cooler. And somewhere about there, these 2 solutions have approximately the same color. And the reason why that's important is that means for me, these 2 solutions have the same concentration of food coloring, because the only difference is they have the same amount of liquid in them. And so right about somewhere in here, you know, right about there, probably, they have about the same concentration of food coloring, okay? Let's do it again with 20 mils. Well, if I do it with 20 mils of bleach, there's more bleach in that container, the concentration's higher. Notice that they hit the same color, not at 40 seconds. They hit the same color sometime around in there. And look at the difference in the 2 times. Here, to reach the same blue food coloring color was 41 seconds, and here it was 22 seconds. Well, if it took less time to reach the same color, that means that the rate is faster here for the 20 mil reaction than it was for the 10 mil reaction. And this is typically the second method that we use to get rate data. And that second method is what's known as the method of initial rates, okay? And in that particular method, what we do is that instead of monitoring the concentration versus time, what we end up doing is we take the graph, say of concentration versus time, and instead of just looking at its shape, what we end up doing is we find the slope of the tangent line at the initial point. And that slope, by definition, since the slope is the change in concentration divided by the change in time, that is the rate of the reaction by definition. So therefore, what we can do is that we can use a lot of different methods to find this initial rate. And this method's actually a little more complicated than just finding the concentration versus time. So what I've done for you is I took our bleach data and I actually found, okay, what the rate was at different times, the rate at which the color was going away at different mils of bleach. And what I want to know is there a relationship between the rate of the reaction and changing the concentration of bleach from one reaction to the next? And the reason why doing it at the initial time is really important is that at time t equals 0, I know what the concentration of my food coloring is, and I know what my concentration of bleach is. At other times down the line, I may not know these concentrations. But if I prepare the solution by adding a certain amount of food coloring and a certain amount of bleach, and I know how many moles, and I know the final volume, I can find the original concentrations. So what I want to know is does the rate depend on if I start messing with the concentration of bleach? Because as we talked about, all right, from what Gavin said before, in this particular case, a higher bleach concentration should make the reaction go faster, okay? So how can we determine that real fast? And notice I've left here a little bit of room for us to do some work on calculating the rate as a function of various concentrations. So here's what I had. I had 10 mils of bleach, and I diluted it to a final volume of 100 mils. And I know that the molar mass of bleach itself is 74.44. And one other thing I should tell you real fast that I did too, is I went ahead and calculated the original concentration of bleach for us. And the original concentration of bleach, it turns out that the bleach I used in my lab, the initial concentration of bleach was 0.8 molar. Okay, it's 0.8 molar. And it depends upon different bleaches have different initial concentrations, but I calculated 0.8 molar. So what I had then done is I took 10 mils of 0.8 molar bleach, and I diluted that to 100 mils of solution. So what I need to know is that I don't really care about this concentration of my stock bleach. I care about the concentration of the bleach in all these other cases. So how can I determine the concentration of the bleach that I started the run with, given the fact I had 10 mils of bleach, diluted it to 100, and the initial concentration was 0.8 molar? Well, in order to do that, I need to know how many milliliters of bleach I actually used in each case. So what I'm going to do is I'm going to say, okay, I'm going to figure out from dilution what happens. And so what I need to do is I'm going to convert my mils of bleach to liters, multiply that by the initial concentration of the bleach, which is 0.8 moles per liter. And right away, that tells me how many moles of bleach I have actually pulled out when I poured out 10 mils. And then I diluted that to a final volume of 100 milliliters or 0.1 liters. And students in particular, I want you to realize we didn't have to necessarily convert it to liters. We could have just said 10 times 0.8 over 100, because the only thing we worry about are the relative amounts. So I diluted 10 mils of 0.8 molar to 100 mils. So that means the concentration dropped by a factor of 10 and is approximately 0.08 molar, okay, from right there. So my concentration of bleach here is 0.08 molar, and I'm only worried really here about, well, 1 or 2 sig figs, okay? I'm not really worried about sig figs from today. This is actually 0.80 if we want to do it, so I have to keep it to 0.080 with these volumes, Well, what would happen if I did it with 20 mils of bleach? Well, notice if I do 20 mils of bleach, the number of moles would be twice as high, and the final volume would be the same. So if the moles are twice as high, but the volume would be the same, this should increase the concentration to 0.16 molar. And if I did it with 30 mils of bleach, it should increase the concentration again and make this 0.24 molar. So the initial concentration of bleach was, in every case, it was increasing from right there. So therefore, here's what I want you to note, and this is where the second method comes into play. Look at the relationships between the rates and the concentrations. Notice that when the concentration went from 0.0 to 0.08 to 0.16, between these two, the concentration doubled. Look what happened to the rate. What's the relationship between 0.043 and 0.022? Well, 0.043 is double 0.022, so this also doubled. And notice here, when I went from 0.08 to 0.24, this went up by a factor of 3, and 0.067 to within experimental error is 3 times 0.022. So notice if I, at the initial time, if for the same initial amount of food coloring, if I doubled the bleach concentration, I double the rate. If I double the, triple the bleach concentration, I triple the rate, okay? So if we go and do some math off of that and look at the rate law, K times the concentration of blue food coloring raised to a power times the concentration of bleach raised to a power. Notice that if I have experiment 1, this would be 0.022 is equal to K times the concentration of blue food coloring to the A times 0.080 to the B. And then the other one, I'm just going to do one of them, 0.043 is K. The initial concentration of food coloring was the same that I started with. And this is 0.16 to the B. Well, if I take these two reactions and divide them, okay, K is the same for the run. Since I started with the same initial amount of blue food coloring, I added that one drop, those disappear. So this number then becomes basically 1/2. And this is equal to 1/2 to the B. So B, turns out that it's 1. So this is the second method we typically use to get rate laws, and this is what's known as the method of initial rates. And both of these methods can be examined on the AP Chemistry exam. It just depends upon the sort of data we have. Personally, I always prefer the graphical method because it's nicer, it's cleaner, it's a little more elegant in terms of the experimentation. But sometimes using this method of initial rates is a little bit easier in terms of grabbing the data, and we've got to understand how to do both as we're moving forward. So graphically, if we're going to do it, we're going to be looking for the graph that gives us typically a straight line. And if we're doing it off of data from right here, I can look at the data and look at the ratios of the data. And from those, I can deduce with a little bit of mathematics or a little bit of logic what the order is going to be. But it is important in this particular case, as we saw, that the blue food coloring stay constant, okay? So we know our rate law. We know our rate law then, okay, is going to equal to, let me go back from right here too, K times the concentration of blue food coloring to the first power times the concentration of bleach to the first power, okay? That's 1/2 of the kinetics problem. The other half now is, how do we determine these with respect to what's known as the mechanism, okay, from right there. And in order to look at that, let's go look at a video. And I want to show you a video of a specific reaction. And Mr. A is going to recognize this, I'm pretty certain, because it comes from our friend Jurgen. Okay, from right there.
Oh, yeah.
And what I want to show you real fast, let me pull it up. Where'd it go? It's right here. Whoops. There we go. Is let's look at a chemical reaction on a molecular level and actually see what's happening from right here, okay? So I hope you can see in the box right on top of that is I've got a chemical reaction here. I'm gonna write this reaction down, okay, so we can see it. And I want the students to observe something specific here. So here's the chemical reaction. I'm gonna write it on my screen. It's 2NO2 plus F2 goes to 2NO2F. This is the chemical reaction we're going to look at from right here. okay? And so I'm going to zoom in on this reaction. I want to show you who the players are in the reaction, okay? For 2NO2 plus F2 goes to 2NO2F. So let me zoom in a little bit here. And I want to introduce you to the players in the experiment. Let me make sure that I've reset this. We're good and ready to go, because I was playing with it before. And let me hide that. Boom. Okay. So let me show you something, because the colors here are kind of interesting, okay? This little guy right here, this is an NO2. And the N has the same color as the oxygen. Don't ask why in that regard. But anything that's a little 3 guy like that, that's an NO2. And right here, the yellow guys are F2s, okay? And what I want us to watch for a minute is I just want us to watch the chemical reaction. And let's see if anything interesting happens in the aspect of the chemical reaction when we watch it, okay? So here we go. And I just want you to pay attention. So let's stop for a second and look right here, okay? Notice something of interest if we zoom in over here. Notice that I have right now my F2 from before broken apart. So if I go back in time and look at it, right there. Notice here, this guy right here, okay, on top of that, was an F2. And it collided with someone. And when it collided, what's left over just became an F atom. Well, that's really interesting. And the reason why that's really interesting is that notice there's no F atom in the expression. The F atom itself isn't here. All my reactants are NO2 and F2, and my product is NO2F. So what's going on here? So let's go watch that little F atom that's highlighted here, and let's see if anything happens to it, okay, moving forward. So let's just watch it and see what occurs. Does something happen to that F atom? Still moving around, right there. Notice what the F atom did. Right there, okay, right here, it collides with an NO2, with a NO2, okay, and became an NO2F. So there it is an NO2 with an F atom, and it became an NO2F. Well, this is interesting because if I let this reaction run for a really long period of time, we'll see these little F atoms pop up. I start seeing these little yellow balls that are moved all over the place. But if I let this reaction run an extremely long period of time, what we will find out is that there won't be any F atoms at the end if we look for a point of time there. So how can it be that there exists an F atom in the reaction as it's going on? There's another one flying off from right there too, but it's not in the overall products, okay? So students, the question I have for you is, can you tell me what the name we give to F is if we're looking at this reaction right here? Is there a name from what you've learned in class, what F actually is? Is there a term that we would give to the name of F, that atom right there? Okay. Well, F itself is called an intermediate, okay, from right here too. And the thing we have to recognize is we have to recognize when we're looking at a chemical reaction, I'm going to bring the text back. When we're looking at the chemical reaction, this chemical reaction actually occurs in 2 steps. In the first step, what happens is an NO2 collides with an F2, and I'm looking right here. And let me change my color so we can see it well. Actually, I'll highlight it. An NO2 collides with an F2 to make an NO2F and an F. So there's one molecule of our product. Now let me make that not white. Hold on one second. There we go. There's one molecule of our product. And notice we make this guy, but then an F later on can collide with another NO2 to make a second NO2F. So if we look, the chemical reaction actually happens in 2 steps. And these 2 steps are called the mechanism. In the first step, an NO2 collides with an F2 to make an NO2F and an F. And in the second step, that NO2F collides with another F to make the second NO2F, which is our balanced chemical equation. It is the existence of the mechanism that doesn't allow us to determine our orders directly from the balanced chemical equation. Because as we said at the very beginning, it's collisions that matter in kinetics. And so what we see here in the mechanism itself, there are two different types of collisions that can result in a product. One of them is a collision between an NO2 and an F2. The other one is a collision between an NO2 and an F, okay, from right there. Well, if we look at any individual step in the mechanism, these steps are called elementary reactions. And what they are doing is they're giving you a blow-by-blow account of how the reaction actually occurs. So an NO2 and an F2 collide and they make product. Well, since we actually make some product as a consequence of that collision, it turns out in that reaction, if I double the concentration of NO2, I will double the number of collisions with an F2. So in an elementary step, because they're actually giving us, hey, step one, two things collide. In that elementary step, we can actually write the rate law from those. But for an overall reaction, we can't, because notice this, since this isn't happening in one step, what it's not saying is two NO2s don't collide with an F2 to make product. What's happening instead is one NO2 hits an F2. Then another NO2 in a later step hits an F. Each of those collisions is mono-y-mono, it's 1-to-1. And so since each collision individually makes products in those elementary steps, we can only look at how affecting the concentration in those collisions affects the overall rate. So if I'm given a mechanism like this as a series of steps, what I have to do in looking at the NO2 reaction, NO2 plus F2 goes to NO2F plus F. And then NO2 plus F goes to NO2F. These two steps, of course, add up to the overall chemical reaction. So what we see here is we have 2 NO2 plus F2 goes to 2 NO2F. So our series of steps, our mechanism, must satisfy two criteria, one of which is it's got to add up to the overall reaction, which, all right, from right there. And we'll see the second one here in just a second. And they do. But the problem is, since they happen with one set of collisions, here's collision 1, and a second set of collisions, here's collision 2, since we actually know an NO2 and an F2 collide, I can actually write the rate law for this step. Rate of step 1 is some K for this step times the concentration of NO2 raised to the first, because if I double the concentration of NO2, I'm gonna have twice as many collisions with F2, times the concentration of F2 to the first. But down here, the rate law would be equal to K times NO2 to the first times F to just the first power. Because in the second step, the collision is only an NO2 and an F. So if I double the amount of NO2, I'll double the collisions with F. If I double the amount of F, I'll double the collisions with NO2, all right? So when you look at a mechanism, you can actually write the rate law for those steps directly from the mechanism itself, because it gives you that blow-by-blow account of what happens. But what's interesting is we have two rate laws, but there can only be one rate law for the balanced chemical equation. So the question is, how do we solve for that? Okay, from right there. And so our last video for the day is to tell us, well, how does the rate law relate for each of the individual steps relates to the mechanism itself? Because the problem is not all of these rates, this rate here and this rate here, which I'll call rate 1 and rate 2, they're probably not the same. So in our last about 7 minutes that we have together, let's look at one more video and then relate it back to aspects of the mechanism. And this is where you're going to kind of get to do your take-home part for a little bit later on. So let's cancel that. We'll leave Odyssey now. And let me go to our last video. And teachers, this video you can find on YouTube. It's a video that many of you may use at school. It's using funnels to look at relative rates of reaction. So what we're seeing right here, and this is off of Flynn's website, I just pulled it off from right here too, is that right now here, what we have are 4 funnels, and each funnel represents one step of collisions in this particular reaction. So this funnel represents a 4-step process. So you could think it is A goes to B goes to C goes to D, and D goes to E. And the final chemical reaction is just A goes to E. And each of these parts here, which I just recognized we didn't actually give the name from before, much like our F from before, that show up in the intermediate steps but don't show up in the final, these guys here are called intermediates. Because there are substances that we make as we go from the mechanism from reactant to product, but they don't show up in our final product. So anything that's created and then is later used up, we call an intermediate from right there, okay? So this step has 4 steps. Now, what I want to think about is, that means there are 4 rates. There's a rate 1, and a 2, and a 3, and a 4, okay? So what I want you to watch right here is watch when Peggy actually runs the mechanism, and I want you to tell me just by watching the funnels, which of the 4 steps is the step that determines the overall rate. So I'm just going to fast forward to the part where she starts to pour in. She talks a lot about the demo from right there too. Okay. So she's about to pour in, and watch the 4 funnels. Which of the steps sets is the slowest of the 4? Whoops. So look right there at what she's done. I paused the video, and just by looking at the sand, which of the rates is the slowest of the 4? And I'll let the video run across from right there. Focus your attention right here. Okay, she goes across. Focus right there. Because if we go back and look at the video, okay, and as we pour through, and she'll start again, watch how the 3rd funnel takes forever to unfill. It's completely filled right now. The other funnels above it are empty, but the 3rd funnel is still almost completely full. And so this funnel is dictating the overall rate of the reaction. The total rate of the reaction can't be faster than the rate of the 3rd funnel. So it turns out when we're looking at aspects of a mechanism, there's always going to be one step, in this case, the 3rd funnel, that has what we call the rate determining step, totally determine the rate of the reaction, okay, from right there too. There's always one step that's significantly slower than all the others. And you'll see Peggy then will flip the funnels around, and then she's going to pour it again. And now that's the slow funnels, the first one. And notice when she pours it again, all the reactants get stuck in the first funnel. And so now that first step, which is just moving the mechanism around, which we can't do in a normal chemical reaction, but here for the sake of discussion, dictates the rate of the reaction. So the second key when we're looking at a mechanism is to recognize we can write a rate law for each step, all right? And one of the steps is going to determine the overall rate of the reaction. So we call that step, the one that's going to determine the overall rate, we call that step the rate determining step. And what's true is that the rate law for the rate determining step must match the rate law for the reaction, because the slowest step in the process has got to be equivalent to the rate that we actually measure in the overall chemical reaction. So to finish our time today, what we'll see at the end of the mechanism mystery is that there are 4, and you can go back and read through this moving forward, because I know we're almost out of time in about 2 minutes. There are 4 mechanisms that we can see from right here. So here's mechanism 1 that one group proposes that says, hey, what happens is the reaction occurs in one step, and in that particular one step, 1 bleach plus 1 blue food coloring yields products. Okay, so it's a one-step mechanism. A bleach collides with a blue food coloring and yields products. In the second step, in the second mechanism, it's a two-step process. In the first step, the bleach breaks apart into some molecule, which we'll call an intermediate, and then that intermediate reacts with the blue food coloring to make products. All right, that's what happens in the second step. In the third mechanism, the bleach then breaks apart to make an intermediate, but then two blue food colorings react with that guy to make products. And then in the fourth mechanism, what happens is that a bleach breaks apart into an O and a Cl minus, and that blue food coloring plus the O makes products. Now, for the interest of time, I'm only going to look at mechanism 4. And let's examine that one real fast before we leave together today. And then you and your teachers can actually do the rest of this and examine these mechanisms as part of your own review moving forward, okay? So I'm only going to examine mechanism 4, and I want to talk about it 2 ways as we finish off. So notice here, we have 2 steps. In the first step, the OCl minus reacts with O and Cl minus. In the second step, then, the blue food coloring reacts with the O to make products. So students, real fast, the first question I have is, looking at this mechanism, would you please tell me what species, what chemical, what atom or molecule is the intermediate in that particular step? Or is there more than one, or are there no intermediates from right there too? If anyone wants to hazard a guess what the intermediate might be. Okay. Well, the intermediate here is going to be oxygen. And the reason why it's going to be oxygen is, notice that oxygen was created in the first step and it was consumed in the second step. So much like our F atoms that we saw in the video from before, that gets created and then it gets used up. So oxygen here is an intermediate. Now, what's interesting is they're claiming that this step is rate determining. So if it's rate determining, let's write down very quickly what the rate laws would be for the 2 steps. So for the first step of the mechanism, since the rate law just involves an OCl blowing apart, if I double the concentration of the OCl, I would double the blowing apart. So the rate law for this first step, for this first elementary mechanism, would just be rate equals K times OCl to the first. In the second step, since it involves a collision between a blue food coloring and an O, I'll call that K1 for the first step, the rate law would be the blue food coloring raised to the first power times O raised to the first power, okay? Now, the people are claiming that the first step is rate determining. What that means is that much like we just saw in the funnels, this step right here dictates how fast the chemical reaction is. So therefore, the rate law for the overall reaction would have to match this, which means that it's first order in bleach. But notice it says nothing about blue food coloring, because since this second reaction is fast, much like the funnel with the large hole, much faster, this reaction happens so quickly, it doesn't impact the rate. So the question is, if this mechanism is correct, the rate law for this step should match the rate law for the overall chemical reaction. Well, what do we see? We know that the rate law for the overall chemical reaction was, go back to our very beginning, OCl is to the first power, but blue food coloring is also the first power. And since these 2 rate laws don't match, that means this mechanism can't be correct. What we have to do is we have to find the mechanism that matches the rate law. So of the 4 mechanisms, it can't be mechanism 4, okay, from right there too. Now, for the rest of this, because we're out of our time for today from right here too, what I'm going to have, and I'm going to, teachers in particular, you'll have this as well, is that you have the handout that goes with the rest of this. So what a great exercise would be for either in class or for the students on their own is that they now can take the other 3 mechanisms, all right, and discuss what's going to happen if they can find a mechanism that balances the rate law. One thing we didn't quite have time to talk about today, but will be in the handout that goes with, is what do we do in the case of equilibrium? So you see from right here too, this step has an equilibrium step, which is an advanced technique when we're dealing with mechanisms, okay, from right there too. And in the handout work that I'll have that accompanies with this, I'll also give Mr. Akimpura a quick video that goes with this that shows you, if you want to show it to your students, how you handle the equilibrium case. It is an advanced situation in mechanisms, showed up on the 2019 exam, question 6, if I remember correctly. But we want to master mechanisms first, where the first step is rate determining as opposed to a latter step with equilibrium. So the video that I'll post forward, that if you want to give it to your students on top of that, or just have them work through if you've discussed that in class, we'll deal with those. But the thing that you guys have to figure out, where we'll leave it right here, we know it's not mechanism 4, which of the other mechanisms, 1, 2, or 3, is our rate determining step, or is it none of them? Have they figured out from right there too? So that's the thing we're going to leave with you to work on your own, which you can do either in class or you can do via Zoom as you continue review for the AP exam. And Mr. A, I'm going to stop from right there and see if there are any questions that faculty or you have or Ms. Clark has moving forward.
Terrific, Paul. And I will post the student materials on the Advanced Kentucky website. Thank you so much. And I'll let you, if you don't mind, send the teacher or instructor copies just directly to the teachers. I think you have all of their email addresses. You can reply all on that.
Perfect.
So perfect. So thanks. That was quite comprehensive, and I hope it was helpful. Kinetics will be an important topic on the AP exam. I think we can say it'll show up.
Oh, I think we guarantee somewhere it's going to show up from right there too. Yeah, we hope. So it's one whole unit, and it's one unit that I know across the board too that you know, you can miss that first time. It's very self-contained, and it's a hard thing for students too because of the mathematics. So hopefully this will allow you guys to go back and maybe 1 class period or 2 class periods and review all those big ideas that go from right there too.
And I like to think that you know, when you have a balanced chemical equation, the reactants is kind of the before and the product shows you the after, but the kinetics is really giving you the during, or what happens to go from, you know, what path do you take to get from your starting point to your final point.
Right.
Kinetics questions will also involve a lot of stoichiometry and a lot of fundamentals. So it's not unusual for a good kinetics question to involve some stoichiometry, some thermochemistry, some gas laws, even some pressure volume relationships. So, but at this point in the year, I hope you students are having a chance to tie different concepts together and really kind of get it. It's not chemistry is not memorizing, but it's kind of understanding. And thank you very much, Paul and Alissa, and thank you teachers and students, and particular students who are here on a Saturday morning. I'm going to cut the recording here and say it's a nice day